Alright, good morning Great Lakes Academy scholars. It is Mr. Manta here once again. And what is today's date? Today's date is Wednesday, April 22nd, and we are moving right along in our chemistry unit. Today is a pretty exciting lesson. We're taking a big step forward in chemistry today. We're going to be done with properties, move on to some cool new stuff. I, for one, am pumped. But we're going to start today with a do now. This will be our last do now. I promise that will be solely about properties because we'll have new material today. Go ahead, get your science notebooks out, create a heading for today, number out numbers 1 through 5 for the do now, and answer these 5 questions that we got right here. Oh, is there a hint in the corner? Interesting. Alright, go ahead and pause the video, answer these 5 questions in your notebook now. Alright, I'm assuming you have now completed that. We're going to unpause and go through our answers. For number 1, the temperature at which butter goes from a solid to a liquid is called its melting point. When something turns from a solid to a liquid, it melts. Like ice melts, butter melts, chocolate melts. That temperature at which it melts is called its melting point. Number 2, the paper clips in Mr. Manta's demonstration were highly magnetic. I was able to pick them up with my magnets. That means they are magnetic. Number 3, electricity can travel through copper easily. That means that copper is conductive. Things that are conductive can transfer either electricity or heat. Number 4, rock, concrete, and diamonds are all types of matter that are hard. We talked about hardness yesterday and how geologists compare whether one rock is harder than another by trying to scratch them with each other. And number 5, potato chips break when you try to bend them, so they aren't malleable. Malleability is that last property that we learned about yesterday that describes how much something can be bent or shaped or changed its shape. Those are the 4 properties we talked about yesterday, and at this point we have talked about so many properties that they add on to what was already a pretty long list. I mean, look at all the properties we have learned. We got what? There's like 18 of them, I think, on this list. It's a lot of properties that we can now use to describe matter. So if we had some sample matter, for example, a giant ice cube, we could describe this ice cube in at least 18 different ways that we've talked about. So let's put it to the side right here and let's run through each of them. Alright, so think about color. I would say that ice cube's color is white maybe, or clear, if you could describe clear as a color, I guess. Its material is that it's made out of ice. It's made out of water ice, specifically H2O. We'll learn what that means later on. Its shape is that it's a cube. Its texture is that it is very smooth and slippery because it's ice. Its temperature is, well, we know it's at least less than 0 degrees Celsius. Because if it was more than that, then it would melt and it would turn into liquid water. So maybe it's negative 5 degrees Celsius, maybe it's negative 100 degrees Celsius, but it's definitely less than 0. Its weight is probably, depending on how big it is, if we say that it's like 1 meter in length, width, and height, then its weight is going to be, I believe, around 1,000 kilograms, because you can calculate that with water. It's one of the cool things about water. Its length, width, and height, well, like we just said, that would be this axis, that axis, and this axis here. Let's imagine that it's 1 meter in length, width, and height. That means that its volume would be 1 cubic meter. Its melting point, since it's made of ice, would be 0 degrees Celsius. Its boiling point, since ice is water, would be 100 degrees Celsius. Oh my goodness, we keep going. Its reflectivity is that it is fairly reflective. It's not as shiny as like a mirror, but you can definitely see that it's bouncing some light off of it down here. Its transparency is that it is pretty highly transparent. You can see through it pretty well. Its hardness is probably that it's very hard. I've never felt soft ice before. Its malleability is that it is very low. It's not very malleable because you can't really bend and shape it like Play-Doh. Its conductivity is that it is not conductive because just plain water is not a very good conductor. And its magnetism is that it is not magnetic because ice is not attracted to magnets. Oh my goodness, that was a lot of properties that we have learned this so far that we can use to describe matter. At this point, you're probably feeling like this kid right here, going, no more properties. Please. Well, folks, I have some good news for you. 2 things, actually. Number 1, we are finally ready to move past properties. I mean, like, we're still going to be using them, but we can start talking about some other interesting things and not just introduce new kinds of properties every single day. And like our friend Barack is saying over here, that is some good news, people. Second of all, it is time to start talking about what happens when you combine substances. And this is kind of the beginning of the really exciting part of chemistry, because combining substances and seeing things happen is what you guys, I think, are excited about chemistry. It's one of the things that I get excited about with chemistry, and it is the basis of experiments like this one right here with this guy making elephant toothpaste, combining different substances and seeing something happen. Now, we aren't doing this today. We aren't doing that anytime soon, but maybe we'll eventually do it. Today, we're going to give an introduction to what happens to when you combine substances. I'm going to give you a couple of today's big ideas before the crash course video. I'm going to step one step ahead of them, which are these two ideas. First of all, that most of the time, when you combine two substances, you get a mixture. If you've been alive in the world, you've probably heard this word mixture before. It's two things that are mixed together. And second of all, in chemistry, there's a special kind of mixture called a solution. Pay attention really close because we're going to talk a whole bunch about what that means to make a solution. We're going to hear first from Crash Course, and while you're watching, I want you to be watching out for the differences between a mixture and a solution. Let's jump over to the video. Oh, right here. Oh, it's not ready. All right. And listen up closely.
Summertime is picnic time with sweet iced tea and yummy fruit salad. And ants. But still, yummy fruit salad. And hey, did you notice something? Those foods have something in common. They're both mixtures. Things made by combining two or more different things. Not the ants, they're just ants. But the iced tea and the fruit salad are mixtures. Anytime you combine two different things, you make a mixture. Whether it's strawberries and bananas, raspberries and blackberries, or cantaloupe and Legos. Which I don't recommend eating, at all. I'm just saying it's a mixture. So let's have a little science with our picnic, shall we? Let's talk about the different kinds of mixtures we can discover. For example, if we mix sand and water in a glass, we'll get a mixture, even though after a while the sand will settle to the bottom of the glass. But if we stir some sugar into the water, the sugar looks like it disappears. But it really doesn't. The particles that make up sugar become distributed or spread around evenly among the particles that make up water. We call this kind of mixture a solution. Solutions have two main parts, the solute, which is the stuff that dissolves, in this case the sugar, and the solvent, which is the stuff in which the solute dissolves, in this case the water. Now, solutions can be
Mr. Manta jumping in here just to say that we're going to spend some time in just a minute going over all those different terms. There's a lot of words here that we don't want to get mixed up. We'll go over them in just a second.
Made from types of matter that are in different states too. For example, the air that we breathe is made up of a solution of gases, mostly nitrogen, oxygen, and carbon dioxide. And soda water is really a solution of carbon dioxide gas and liquid water. But no matter what, and this is important, mixing things together in solutions does not make a whole new substance. Solutions can be separated again, back into the substances that made them. So, for example, if you leave the lid off a bottle of soda water, the carbon dioxide that's dissolved in the water will slowly float up to the top and bubble away. Given enough time, you'll be back to having plain old water in the bottle and carbon dioxide in the air as two separate things, not mixed together. So when you take a sip of your favorite fizzy drink, you're drinking a solution. But not all substances dissolve easily into other substances. The ability of something to be dissolved is called its solubility. Sand doesn't dissolve in water, for instance, so we say it has low solubility in water. But sugar dissolves pretty easily, so sugar has high solubility in water. Still, no matter how easily something might dissolve into another thing, you'll eventually reach the point where it can't dissolve anymore. Let's say you pour a whole bunch of sugar into a small glass of water. If you keep adding sugar to it to make it even sweeter, and who would blame you for trying, you'll get to a point where no more sugar can dissolve. The extra will just sit at the bottom. This is called saturation, the point at which no more solute can dissolve into a solution. Saturation happens when there's just no more room for the particles that make up the solute, in this case the sugar, to squeeze between the particles of the solvent, the water. Whew! All of this is making me snacky. Let's check out our picnic table again and investigate the different kinds of mixtures we see there. Let's start with the fruit salad. That's definitely a mixture of different kinds of fruit. Is it a solution? Nope, because the particles that make it up aren't equally distributed. I can dip my spoon in there and come up with nothing but strawberries one time, and then go back for more and get a spoonful of only bananas. How about the sweet tea? The solution to that question is that it's a solution. Particles of, say, water and sugar in the tea are evenly distributed in the glass. Every bit contains water and sugar. They're spread out evenly. Now, can the substances that make up our iced tea solution be taken apart again? Yep, if we heat the tea so that the water in the solution changes from a liquid to a gas, it evaporates into the air, leaving the sugar behind. So let's go over what we learned at our little mixed-up picnic. A mixture is made by combining two or more substances. When the particles that make up the substances are equally distributed, the mixture is called a solution. Solutions can be made of substances that are in the same state of matter, like gases in the air, or in different states of matter, like the gas bubbles in soda. The solute is the part of the solution that is dissolved, and the solvent is the part into which the solute dissolves. And solutions and some other kinds of mixtures don't always make new substances, even though it might look that way. Now, let's enjoy what's left of our picnic before the ants carry it all away.
Alrighty, as usual, they go through a whole lot of information and they do it pretty quickly, but we're going to run back through all of that ourselves. Alright, let's start to recap. We're going to take away 3 main key points as usual from our crash course video, and the first one being this. Yes, you should write this down in your notebooks. Most of the time, when you combine 2 or more substances, you get a mixture. There's all kinds of examples of mixtures that I can think of, that you can think of, that you've seen throughout your life. So for example, if you've ever gone to a soda fountain, I remember when I was like in 5th and 6th grade and I would go to a soda fountain, I would take my glass and I would like get a little bit of cherry Coke in it, and then I'd move it over and I'd get a little bit of Diet Coke, and then I'd move it over and I'd mix in some Sprite and create like some terrible mixture of all the different flavors inside of it. That's an example of a mixture, multiple things mixed together. If you or your parents has ever bought a giant bag of different kinds of candies like this is a mixture of different kinds of candies. There's Twix in there, and there's Milky Ways, and there's Snickers, and the Three Musketeers, all mixed together. And the example that they use in the video is the fruit salad, right? So we have all these different kinds of fruits mixed together. Man, that one looks really good. That makes me wish it was summer and we can have barbecues again. But anyway, moving on from there. Our second key point, though, is that a solution is a special kind of mixture where the particles are evenly distributed. Now, you might see that word solution and be thinking like this kid. You mean like the solution to a math problem? And to that I would say, no, not like a math problem. It's a very different kind of word, solution, and I want you to get the whole idea of the solution to a math problem out of your head. It's a totally different use of this word solution. Instead, what we're talking about here is a special kind of mixture where the particles are evenly distributed. So in the video, they compared. They said, if you try to mix sand into water, it doesn't really work very well. The sand just kind of keeps clumped together at the bottom of the glass. But if you pour a bunch of sugar into water and then stir it around, something very different happens. And the sugar dissolves into the glass. It spreads out evenly throughout the whole glass. And eventually it breaks down into such small particles that you can't even see the little grains of sugar anymore. It becomes totally dissolved into the liquid, and those little grains disappear. It becomes evenly distributed. That means that over here on the right, this is a solution, where the particles of one thing become evenly distributed into another. This is not a solution, because all the dirt is clumped up at the bottom here, whereas the sugar is evenly spread out throughout the water here. Alright, pause for a second to complete classwork question 1. It is, in your own words, what's the difference between a regular mixture and a solution? I'm now going to move on, assuming that you've completed that either in your notebook or in the classwork questions. Pause right here if you need to. I'm moving on. Alright, I do want to add a quick side note, which is something that I always wondered when I was in 5th grade, when I was first learning this kind of stuff. Most of the time, when chemists, that's scientists who study chemistry, when they talk about making solutions, they're dissolving a solid into a liquid. So really you could make a solution, and I looked this up to make sure, you can make a solution where you mix a gas into a solid, or a liquid into a gas, or all kinds of different solutions, but for the most part we're talking about dissolving a solid into a liquid. Now, you probably have experience with this. For example, if you have ever made Kool-Aid with one of these little packets, or like iced tea or lemonade with one of these little flavor mix packets, you've dissolved a solid into a liquid. What you do is you take that packet and you pour it into some water, like this here, and then you stir it around a whole bunch, and eventually it becomes kind of spread out, it changes the color of the water, and it breaks down into such small little particles that you can't even see them anymore. This is a case where you're dissolving a solid, like the Kool-Aid or the little crystals here, into a liquid, which is the water that you have. Another example, if you maybe don't do this, is these bath bombs that I know have become very popular now. I've never actually used one myself, but I think the idea is that you buy one of these things and you take it and you put it into the bathtub, and then it like explodes out in color, and all the stuff that makes up the solid bath bomb dissolves out into the water. and spreads out evenly and colors your bath water so that it's like bright blue or whatever color you want it to be and all bubbly and nice. These are both examples of solids dissolving into liquids to create a solution. Alright, the third key point that I want to make here is the vocabulary, the words that we use when we're talking about solutions. These are very important. We don't want to get them mixed up because when we're talking about solutions, there are these same kind of 3 parts every time for every single solution, and so scientists are very careful to use the right words to describe each of the different parts. Here's what I mean. In this little demonstration over here, somebody is taking some salt, like just some regular salt you use for dinner, and they're dissolving it into water. Anytime that you have a thing that you're dissolving into another thing, like in this example, the salt, the thing that's being dissolved, is called a solute. S-O-L-U-T-E, solute. Anytime that you're doing this, you have a solute, which is the thing that's being dissolved, and you have like the liquid or the bigger thing that the solute's being dissolved into. So in this case, the water is that, and it's called the solvent. You have a solute being dissolved into a solvent. That's the salt being dissolved into the water. The solute and the solvent. Yeah, they sound very similar. Yes, it's on you to keep them from getting mixed up in your brain. At the end, after you've mixed these two things together, what you have is called the solution. So they've created salt water, basically in this case, and that is an example of a solution. One substance dissolved or mixed evenly into another. And you have the solute and the solvent and the solution. Yes, you have to remember what each of those means. I know that you all are dying. You're like, Mr. Manta, I need a definition that I can write down in my notebooks. So we're going to go through some definitions right now. Yes, you should be writing each of these down. First off, we have this word dissolve that I keep using. Dissolving is a verb. It just means when a solid is mixed into a liquid and breaks down into its particles. So all these examples that we've been looking at here are examples of things being dissolved. Second of all, we have this word solute. That is the substance being dissolved, like the Kool-Aid packets or the salt or the sugar or whatever it might be that's being dissolved. Third, we have the solvent. That's the liquid that that thing is being dissolved in. Usually that's water, but in theory you could use, I don't know, oil as a solvent or some other liquid. Lastly, I won't say lastly, next we have the solution, and that is the name for the final mixture of the solute and the solvent combined. Those two things together are a solution. Next we also have this word called saturated. She mentioned this in the crash course video. When a solution is saturated, that means that the solution has the maximum amount of solute possible dissolved in it, and you can't dissolve anymore. So the example that they gave in the video was if you just took a cup of water and you poured sugar into it and you dissolved it, it would dissolve. And if you just poured more sugar and more sugar and more and more and more, eventually it would reach a point where it can't dissolve any more sugar, and you would just get like solid sugar clumping up at the bottom. That would mean that your solution is saturated. Prior to that point, when you're still mixing it in, it's unsaturated, and then once you get there, it's a saturated solution. And lastly, they also use this word in the video called solubility, and that's kind of a measure of how much a given substance can be dissolved in a solution before being saturated. So like, I think they said that sand has very low solubility because it doesn't dissolve very much, but sugar has very high solubility because it can dissolve in water very easily. If you need to, pause the video right now and write down these 6 definitions in your notebook. Make sure especially not to get these 3 mixed up. Alright, one other side note I want to add in, which is that the way that solutions work is that if you could zoom in super close onto a solution, what you would see is particles of solute spread out evenly among particles of solvent. When you have a solution, things like salt or sugar, they break down. Even those tiny little grains of salt break down into their very smallest possible particles. So like if we'll say that this is salt water, and what you have is these tiny little, so small you can't even see them, particles of salt dissolved in the water. And if you had a microscope and you could zoom in super duper close, you would see something like this. You would see all these the blue ones here are water particles. There's regular particles, swimming and flowing all around each other. And the yellow ones here are, we'll say, salt particles. And the reason that this is a solution is because the particles are evenly mixed together. They're all perfectly mixed in. They aren't kind of clumped up. You don't have a big clump of salt all together down here in a salt rock. Instead, they're all spread out throughout the water. That's why it's a solution. Again, in this case that they showed in the video, this is not a solution because the sand is just all clumped up together. It's not evenly spread out. But this here is a solution because the sugar is spread out evenly. Alright, now we get to have another demonstration. We're going to have more and more of these going forward, which I'm very excited about. I'm going to do a demonstration here. I'm going to pull up my video in just a second. And I also want to add, though, if you can convince your parents to help you do this demonstration at home, and you can send me a picture, I will totally shout you out in the next video. In fact, you might even get onto the Great Lakes Academy Instagram, which is very exciting. This is a very easy demonstration to do, and we're going to have more and more kind of chemistry demonstrations as this unit continues to move forward. This is probably the easiest one to hop onto if you want to take part with me. All you need to do this demonstration are these 4 things. First of all, you need half a cup of water, so hopefully mom or dad have a set of measuring cups. And you can grab the one that's the size for 1/2 cup and fill it with water, just like room temperature water. Make sure it's not too hot, not too cold, just a regular temperature. You'll need 2 tablespoons of salt. Hopefully mom or dad has measuring spoons like this. You want to get the one that's the size of a tablespoon and get salt that you can measure with that tablespoon. You'll need a glass, and you'll need something to stir with. It's a pretty simple demonstration. I'm going to go ahead and open up my camera. Hey folks, how are you guys doing? It's Mr. Manta here. Yes, it's really me behind all these videos working at my computer. And I want to show you guys what I got for this demonstration. So, I'm going to take my glass that we're going to be working with. I have some salt. I have some water. And I have all the stuff that I need to measure things out. So I have, this is a 1/2 cup measure. You'll need to find one that's about this size as well. And these are my measuring spoons that I stole from my mom. I will need to use the tablespoon measure today, which is the biggest one usually if you have a set of measuring spoons like this. Here's what we're going to do. Scientists have determined the solubility of salt in water. That means how much salt can be dissolved in water. And specifically what they figured out is that if you take 1/2 cup of water, a little bit less than 1/2 cup we'll do today. So I'm going to fill up this 1/2 cup, but not quite all the way. And you dissolve 2 tablespoons of salt in it, then it will be perfectly saturated. That means that you can't dissolve any more than 2 tablespoons into 1/2 cup of water. So, let's get started. I'm going to be very careful to make sure I don't spill here because my mom just walked by. She doesn't want me to make a mess at the work table. So, I'm taking my water. This is just room temperature water, not too hot and not too cold. I filled up my 1/2 cup just a little under all the way. And I'm going to pour it into my glass of water. Simple enough. I am then going to take my salt, and I can never get these open. This is just regular salt that you would buy at the store that mom or dad probably use for cooking. And I'm going to take my tablespoon measure, that's the biggest one that I have, and I'm going to measure out first 1 tablespoon of salt. So I want to have it full, kind of all the way to the top of the tablespoon, but not overflowing at all. So there's 1 tablespoon. And I want to take a 2nd tablespoon as well. And once I have done that, I can put the salt, the water, the tablespoons, all that other stuff to the side. Now, at first, if you look really closely, hopefully it shows up well on the camera, what you can see, maybe you can't see it super well, but I can definitely see it here, is that I have a whole bunch still of solid salt that's down in the bottom of this, and then some water with salt dissolved into it. But because I measured everything out correctly, if the science is right, I can mix all of this up to get the solution to the perfect point, get the solution just to the right point where all of that salt dissolves in the water, and I have no more solid salt in the bottom of this glass. Let's see, I'm mixing it up here. You can use a fork, a spoon, whatever you like. And I think I did this just right. So now that I've mixed it up, the salt is fully dissolved into the water. And if you look closely, you cannot see, if you look closely, there is no more solid salt down there on the bottom of the cup. It is all, I might have had just a tiny bit too much salt. It should be all just perfectly dissolved though, right at that exact point. There's no more solid salt there down on the bottom. It is all dissolved into the water. That means that right now this is a solution and it is saturated. That means it can't dissolve anymore. So, for example, if I took another tablespoon and I got my salt back out, and I tried to mix in 1 more tablespoon here. Let's see what happens. I'm going to mix it in, doing the same thing that I just did last time, but this time, oh man, no matter how much I stir, I could stir this for days and days and days and days, and I would never be able to change the fact that there's a whole bunch of solid salt in there at the bottom of my solution. No matter how much I stir, this solution is already saturated. It already has the maximum amount of salt dissolved into it. And so what you can see, again if you look closely, is now I'm just getting a big layer of solid salt down there at the bottom, and it won't dissolve into the water anymore. That's because this solution is saturated. And scientists know the solubility of salt in water, and so I knew I had to add exactly 2 tablespoons into a half cup of water in order to get a perfectly dissolved solution. I challenge any of you out there to somehow make a solution of water and salt that can hold more than 2 tablespoons. You can't do it. It's just a property of the world. It's the way that salt and water work. And yes, if you want to, you can try taking a sip of this, and it would taste awful, disgusting. I'm not going to do it. I'm not going to do it because it's going to taste really bad. Don't like drink a whole glass of it because that would probably make you sick. But you can take a sip of it just to like be weird, see what it tastes like. All right, bringing it back now. Ooh, yes, bringing it back now. I want to follow up with today's second classwork question, which is, in Mr. Manch's demonstration, the one I just did, what was the solvent and what was the solute? Go ahead and answer that in classwork question 2 now. And I'm assuming we're unpausing and moving right along for our last part of the day, which is always our independent practice. Go ahead and write out numbers 1 through 8 in your notebook now. And here are your 8 questions. Pause the video, answer these 8 questions independently in your notebook now. I'm now going to unpause, or assuming that you are unpaused, if you answer these 8 questions, because our answers are these. Number 1, anytime you combine 2 or more things, you create a mixture. Some of you probably said solution because we keep on talking about solutions, but a solution is a special kind of mixture. Every time you combine 2 or more things, you always create a mixture. For number 2, the answer is solution. A solution is a special kind of mixture where the particles are evenly distributed. Number 3, in Mr. Mancha's saltwater demonstration, salt was the solute. Number 4, in Mr. Mancha's saltwater demonstration, water was the solvent. Number 5, in Mr. Mancha's saltwater demonstration, the salt water he had at the end was a solution. That means it's the 2 things mixed together. Number 6, when you can't dissolve any more salt into a solution, that means the solution is saturated. It has as much solute as it possibly can in it. Number 7, sand doesn't dissolve in water very well, meaning it has low solubility. And number 8, a solution is just a mixture where the particles are evenly distributed. That's the difference between a regular mixture and a solution. Alright, go ahead, start the questions you got right, fix the ones you got wrong. Let me know in the classwork questions which ones you did get correct. And we're going to go ahead and wrap up for today. That's all we got. Move ahead to the exit ticket. I look forward to seeing who is able to do this demonstration at home, to see if they can dissolve more than 2 tablespoons of salt in water. And you can't. And send me a picture. And of course, the last thing I always want to shout out is today's cool thing. Today is a very fun one. It is maybe my favorite website on the entire internet. You know, a lot of websites, they try to do too many things. They have like videos and chat rooms, and that's too many things. This is a very simple website. It's called howmanypeopleareinspaceriightnow.com. And all it does is it tells you how many people are in space right now. You can go there yourself and you will see any given day of the year how many people are in space. Right now there's 3 of them. You can even see their names, the countries that they're come from, where they are in space, all kinds of fun stuff like that. Alright folks, that's all we had for today. Knock out that exit ticket in classwork, and I will talk to you guys tomorrow.